Hello everybody, hope you had a good week. Welcome back to video number 9. This is our last video reviewing gas laws. So this is wrapping everything up from the end of March all through April on gas laws, putting everything together. Next week we'll start our new unit on acids and bases, but this one's just going to be a review of everything that we've learned. So let's start with today's warm-up. All right, for today's warm-up, a multiple choice question. Which of the following changes to a system will not result in an increase in pressure? And think about why. A, increasing the volume. B, raising the temperature. C, decreasing the volume. Or D, adding more gas molecules. Which one of these would not result in increasing the pressure? Take a second, pause, and try to answer. All right, so let's talk about each of these. Increasing the volume. If I make the volume bigger, what's going to happen to the number of collisions that those particles have with the wall? Remember, you could imagine kindergartners running around in a room. Okay, if I increase the room that they're in, is there going to be more or less collisions with the wall? Hopefully you say less. So what's going to happen to the pressure? It's going to go down. So the correct answer is A. Increasing the volume will decrease the pressure. Why? Because there's fewer collisions per unit of surface area. And this is also called Boyle's law. If we look at the other choices, raising the temperature, those particles move faster, hit the walls more often with more force, increasing the pressure. Decreasing the volume makes the room smaller, so they're going to have more collisions with the wall, increasing that pressure. Adding more gas molecules, again, more collisions with the wall because there's more particles. There's more things moving around in this small area. Okay? We're going to do a couple warm-up questions just to begin our review, and then we'll focus on the review worksheet that is today's homework. So, we could call it Do Now number 2. A sample of hydrogen gas is held in a 1-liter metal cylinder. At what temperature will it exert the greatest pressure? So this goes back to last video where we imagined how does temperature affect the speed of particles. Take a second, pause. Hopefully you're thinking C, 55 Celsius because it's the highest temperature. Highest temperature, particles move the fastest. They're going to run into the walls with the most force, causing that greatest pressure. All right. Question number 3. 12-gram sample of gas occupies 1,000 milliliters at STP. What is the molecular weight of that gas? So we're going to walk right through this one because this is going to be the main problems we're going to focus on in this unit, okay, or in this this video, where we're given variables and we're going to use those variables to solve for unknowns. So anytime I'm given variables, the first thing I like to do, remember, is list them. 12-gram sample, that's a mass. 1,000 milliliters, that's a volume. Now remember, in this unit, my volume typically is going to need to be in liters, so I right away converted that to liters by moving the decimal 3 places to the left. My temperature is 273 because it's STP. My pressure is 1 atm. Now I'm looking for molecular weight or molecular mass. I would look back maybe in my notes or my previous worksheets and ask, do I have an equation that I've used that allows me to calculate this? And I do, and it looks like that. Molecular mass or molecular weight equals MRT over PV. So what I need to do now is plug in my variables to solve for that unknown. In this case, it's already rearranged to solve for what I want. The only variable I'm missing, however, is R. And remember, R is a constant that is dependent on pressure. Because my pressure is in ATMs, I'm going to use 0.08206 for R. So I've plugged my variables in. I go ahead and solve, and there is my molecular weight or my molar mass. This was the main types of problems we've saw this unit, where we're given variables and asked to solve for unknowns. A lot like you're doing algebra class, but now we're applying that to the behavior of gases. Okay? Now when we're describing behavior of gases, you should be able to imagine those gases. Even though we can't see them, you are always asked to explain their behavior. So what happens to pressure when the temperature is cooled, and why? So what I want you to think about is what happens to gases when the temperature goes down. Do those particles speed up or slow down? Now again, I always use that analogy of kindergartners, okay? And temperature is a lot like sugar. If you add temperature, you add sugar, what happens? Do they move more chaotically, faster, crazier? Yes. If I take that away, okay, they're going to calm down more typically. Just like temperature. Temperature is cooled, particles slow down. So what's going to happen to pressure? It's going to decrease because there's less collisions, and those collisions aren't as forceful because the particles are moving slower. All right. One more variable problem. Let's walk through it before we get to a few that we're going to look at on our review. Remember, anytime you're given these variables, I first like to list them and then figure out what gas law I'm going to use based on what variables I'm given. A small sample of helium gas occupies 6 milliliters. So that's a volume. If you wanted to turn it to liters, that's fine. But milliliters in this case is just fine. At a temperature of 23 degrees Celsius, this unit, I'm always using Kelvin. So all of my degrees Celsius, I turn right away to Kelvin. At a volume of 9 milliliters, what temperature does the volume expand to 9 milliliters? So I'm looking for temperature. Okay, so again, I've listed my variables, and I've listed what I'm looking for. Then I can go through and identify what gas law do I use? Charles. Because I'm given volume and temperature, I need to use Charles' law. And that's what Charles' law looks like. Then I need to rearrange Charles' law. Remember, this takes some extra cross multiplying because I'm looking for a variable on the bottom. So I move T2 to the top over here, and then move everything else over. So I move T2 up here, and then move, I'm going to draw it so you can see it, okay? So I move T2, I cross multiply it up here, because I can't solve for a variable on the bottom, and then I move everything else over. So then I'm going to move T1 to the top, okay? Remember, I've crossed out T2, and I'm going to move V1 to the bottom. So this one takes a little bit extra to rearrange because I'm solving for a variable on the bottom, and it ends up looking like this. V2 times T1 over V1. So now I can go ahead and plug those variables in. In this case, the milliliters cancel out, so it didn't matter that I converted it to liters, and I end up with an answer of 375 kelvins. So 2 things I'm going to ask you in your review assignment. I'm going to ask you what gas law did you use and what is your answer. Okay? Now remember, the gas laws, if you don't know what they are, worth writing down. These are the gas laws we are going to use to solve our problems today. Okay? Boyle's law, remember the relationship between pressure and volume, inverse. As pressure goes up, volume goes down. Charles and Gay-Lussac's law, they have a direct relationship, volume and temperature. As temperature goes up, volume goes up. And as temperature goes up, pressure goes up. The combined gas law just relates all of them. And it takes into account when all of these variables are changing. The ideal gas law, when I'm looking for moles, I typically use, or if I'm only given one pressure or one volume. And then my molar mass equation. Molar mass equals MRT over PV. This is the same equation, just rearranged slightly differently. Okay? You should also, again, be able to imagine gases. So when I imagine gases, even those gases in the room around me, I need to be thinking of these particles moving like this, chaotically. In no particular order, they're bumping into each other, they're all over the place. So they fill up the container that they're in, they're flowing around chaotically, they have a very low density, they're very spread out. I can push them closer together because they are spread out and they fuse and diffuse. And that was my video last week, going over how gas particles spread out, essentially randomly. But who moves fastest? Hot particles and small particles. Okay. We should also be able to explain the kinetic molecular theory. And this describes the motion of molecules and the fact that they're always in motion. And the individual particles are so small, I can ignore those particles. The size of the particles anyway. Now they actually have some volume, but at this level in chemistry you can essentially ignore them. What causes pressure? Collisions. They run into each other, they run into the walls of the container, that's what causes pressure. They exert no forces on each other. Some of these pieces of the kinetic molecular theory aren't true. That is one of them, along with the volume of particles is essentially 0. They actually have volume, but it's very small, and they have forces with each other, but it's very small. Gas particles are moving so chaotically, they don't really stop to say hello. Okay? They're flying past one another. Technically, depending on the particular gas, this may affect some behaviors, but at this level we can ignore it. And the average kinetic energy is proportional to the Kelvin temperature of a gas. So as temperature goes up, kinetic energy goes up. And these are just things that we've learned this unit that are going to help you answering your review questions today. This is kind of summing up the gas laws. So when we're summing up these gas laws, the first thing I asked you to do on the review is fill in the blanks on our learning objectives for this unit. And this is oftentimes the most common questions I get from this review. So we're going to do this first section together. And it is just looking at all of the things that I expect you to know about gas laws from this unit. You should know that random motion of molecules and collisions with surface area cause what when it hits, cause what on the surface? Blank. Okay, so they create what on the surface? So when things collide, what does that create? Hopefully you say pressure. That creates pressure. When something collides with a wall, that creates pressure. You should also know that blank motion of molecules explains the diffusion of gases. Is it a motion that we really know about? Explains that gases move chaotically? No, it's the fact that molecules move randomly. So you know that random motion explains diffusion, and that's why gases spread out. That's why over time, if you light a candle, you're going to smell it on the other side of the room because particles move chaotically. Okay? If you put a Kool-Aid packet into a pitcher of water, naturally it will mix. Okay, you don't necessarily need to mix it up. You can speed it up by mixing it up, but naturally, because molecules move chaotically, it will mix, it will diffuse. And the rate of diffusion can be controlled by temperature. Does it increase or decrease as temperature increases? And you should say increases. As temperature goes up, rate of diffusion goes up. What about small molecules? So small molecules diffuse faster or slower than large molecules. Hopefully you say faster. Small molecules typically move faster. What about when I'm comparing different particles? Who's going to move the fastest? The heaviest or the lightest? So here it says, which of the following molecules will have the highest speed? O2, CO2, HCl, or N2. Well, what would I need to get? I would need to get the mass of those substances, because in the last question we just said smaller molecules move faster. So if I look at the molar mass of all of those particles, which one is the lightest? Nitrogen. And then learning objective number 3 says students know how to apply the gas laws to relations between the pressure, temperature, and volume of any amount of an ideal gas or mixture of ideal gases. That is using your gas laws. So we don't need to fill in any blanks there. But we do have a few more fill in the blanks with the numbers 4, 5, and 6. This unit, you also need to know the values and meanings of standard temperature and pressure, or STP. Hopefully you know the standard temperature means 0 degrees Celsius, which is also equal to 273 kelvins. Standard pressure is 1 atm, or 101.3 kilopascals. That equals 760 millimeters of mercury, which equals 1 atmosphere and 760 torrs. Also, what volume is occupied by 1 mole of any gas at STP? We've been using this for the last few units. 1 mole of any gas at STP has a volume of 22.4 liters. You should also know how to convert between Celsius and Kelvin. Remember, if you're going to Kelvin, you always add. What is that magic number you always add? 273. So 100 plus 273 is 373. Now, if I'm going from Kelvin to Celsius, I subtract. 400 Kelvin minus 273 is 127 degrees Celsius. If I'm also going from Kelvin to Celsius, I subtract 273. 150 minus 273 equals negative 123 degrees Celsius. Remember, you can have a negative in degrees Celsius, degrees Fahrenheit. We're all familiar with that living in Wisconsin, but you cannot have a negative on the Kelvin scale. That's the purpose of the Kelvin scale, is it takes into account the fact that molecular motion theoretically stops at 0 Kelvin. That is where temperature begins. You can't get colder than that. So 0 Kelvin is also called absolute zero, and at 0 degrees Kelvin, or excuse me, it's just kelvins, it's not degrees, 0 Kelvin, all molecular motion theoretically stops. I say theoretically because it's never been reached, and the kinetic energy is 0. Okay? All right. So those are the learning objectives I want us to be familiar with, and this is what you need to understand moving on from this unit. Okay, and you're going to use this unit depending on if you come back to chemistry in a year or two, or if you move on to physics or different math classes. You're going to use this in your future. All right, so let's do a couple review problems just so you understand how to answer these questions. Let's do review number 1, and I think we're going to do number 5 next. So number 1, a balloon has a volume of 3.5 liters at 21 degrees Celsius. When the air pressure is 1.05 atms, how many moles of gas are contained in the balloon? What law does this follow? So again, I like to list my variables. 3.5 liters, that's a volume. 21 degrees Celsius, that's a temperature. But again, I convert it to Kelvin. 1.05 atms, that's a pressure, and I'm looking for moles. So what law do I use here? Notice, this should say T1. Let me fix that. Sorry, there's a small typo. I'm going to fix that. This should say T1. That's a T, not a V. Okay? So notice I am given only volume, temperature, and pressure. Okay? I'm not given a V2 or a T2. So if I don't have a V2 or a T2, if I have nothing to compare it with, what gas law do I use? The ideal gas law. And that's one half of your answer, because the question also says, what law do you use? So I'm using the ideal gas law, PV equals nRT, where I'm solving for N. So I need R. To figure out which R do I use, I look at my pressure. Remember, my pressure is an ATM, so I'm going to use 0.08206. I rearrange my equation to solve for N, and then I plug in my variables. Once I plug in my variables, my units cancel, and I end up with 0.152 moles. So my answer is 0.152 moles. The gas law that I used is the ideal gas law. Please, please, please show your work here. Okay, so that's number 1, a lot like the other problems you're going to be doing. Let's do another one, number 5. At constant pressure and 25 degrees Celsius, what's that? That's a temperature. Okay, looks like I went a little out of order here. A sample of gas occupies a volume of 4.5 liters, so that's a volume. So notice how I'm listing my variables, my temperature in kelvins, my volume in liters. Okay, this should say liters, another typo. I'm sorry for all of these typos. Okay, so this should say liters, not milliliters. All right, anyway, at what temperature, so I'm looking for T2, okay, will the gas occupy a volume of 9 liters? Again, it shouldn't say milliliters, that should say liters. So sorry about that. So here are my variables. Notice I'm giving a V1 and a V2, a T1 and a T2. So I'm not going to use the ideal gas law. I'm going to use Charles' law, which says V1 over T1 equals V2 over T2. So now I rearrange just like I did earlier in that review problem. Remember, this one takes a little extra rearranging, and I solve for T2. T2 equals V2 times T1 over V1. I plug my variables in, and I end up with a temperature of 596. The two pieces for this answer are, what gas law did you use? Charles' law. What temperature? 596 kelvins. Okay? So those are the first, I think, 9 questions or so on using the gas laws mathematically. The bottom half, the 10, 11, 12, forget how many questions there are kind of explaining how these gases behave using the kinetic molecular theory. So explain the following observations using the kinetic molecular theory. That is, how do gases behave? So a balloon of gas is placed in a car. It gets larger. Why? So what do I know about if it's placed in a car, it's heated up on a hot day? So those particles are going to be moving faster or slower. You should say faster. So are they going to be running into the walls of the balloon harder or softer? You should say harder. Are they going to be hitting the walls of the balloon more often or less often? You should say more often. So what's that going to do? That's going to cause the force to increase. So air temperature increases inside the balloon. Those particles move faster. They hit the walls of the balloon more often with more force. This increases the volume, also known as Charles' law. And this happens in a combustion engine. Okay? The gas particles are heated up, push the piston up, increasing that volume. Okay? All right. Number 11. Organize the following gases in order of their rates of diffusion from slowest to fastest. So who's going to move the slowest? Heaviest or lightest? You should say heaviest. So what I would do is I would go through and calculate the molar mass of all of these gases. Who's ever the heaviest is going to be listed first. Who's ever the lightest is going to be listed last. Okay? And it ends up being here. Okay, carbon dioxide, I think, has a molar mass of around 44. Oxygen's around 32. Ammonia is around 17. And hydrogen is around 2. Okay, grams per mole. So explain why you chose the order. Heaviest move slowest. Lightest particles move fastest. All right, so hopefully that was a great review, kind of refreshing your memory on gas laws, giving you the skills necessary to answer the rest of those gas law review problems. So that's your homework for this week, is to finish that review, show your work, and share it with me hopefully by Friday so that we're ready to start our new unit on acids and bases next week. So great. I look forward to seeing you all in the meeting. Hopefully this made sense. If you have any questions, please reach out, and I look forward to hearing from you and seeing you soon. Bye.